Electronics. Ma'am, with great pleasure, I invite you to deliver your session. Over to you, ma'am.
Thank you, Ujwala madam, for your introduction. So, good morning, everyone. Today, I am here to present for this FDP, which is organized by the Mega College of Engineering. The topic is mainly for this FD. They have organized the FDP on the advanced semiconductor technology. In the part of advanced semiconductor technology, my topic is based on the nano semiconductor devices and their applications. So, as we know, worldwide there is a lot of growth is present in the semiconductor industry, and our government is also planning mostly on the IC semiconductor industry, which is going to be $1 billion industry and very useful, which is going to provide economy to our country and providing opportunities to many of our in the world. So I think it will be useful for those who are present. So
Vanita madam, unmute yourself. Vanita madam, unmute yourself.
sir, is it okay?
Yes, ma'am.
Okay. So, good morning again, everyone. So, today I am going to discuss a topic on the emerging devices which is going to rule the present in industry, semiconductor industry all over the world. Those nothing but nano devices and their applications. I'm working. I'm working as assistant professor in AC department, MGIT Hyderabad, and I have done lot of research in this topic which I have done, and I worked as a research engineer in the design and testing of antennas. So practical exposure I have on the electronics field and communications. So I think I can do as much as possible justice. Everything is ocean, so we are going to learn a drop in that. So as much as possible, I will try to contribute that. So my outline will be based on the introduction, why we have chosen this one. Before going to the nano devices, we should know what are the drawbacks of the MOSFETs which is present and why it is made to come into the nano devices. The nano devices presently ruling the world is nothing but FinFET, gate all around FET, nanowire FET. And what are the reliability in the application session? What are the reliability analysis present in the FinFET based domino logic circuits? How we are going to vary the dynamic and static power dissipation of multipliers, which is made use of FinFET and FinFET based SRAM circuits. So next is, so main our purpose is the world is back of reducing the power consumption of any devices which we are going to use in our present technologies, that is nothing but IoT, artificial intelligence, cyber security, and whatever the climate changes which we are facing all over the world. So that is a climate change is a major problem which is we are facing, and we as the intellectuals we need to provide the solution for the problem which we are facing. So here in this one, when whichever the devices we are using, the climate changes or IoT or AI, the main problem which is facing nothing but power consumption is going to be more. If more power is present for any devices, what is going to happen? The natural resources which are present, the water and the whatever the pollution is there, that is going to be created more. So if you reduce the power, we can overcome the doing harm to the natural resources. So here in this one, our main challenge is reducing the power consumption for designers to have the portable devices and memory circuits, which is useful for the latest technology which the world is going through. going through this. So the major motivation of this topic is chosen is, as we know, the world is back of AI, robotics, IoT, and cyber securities and environment challenges. So we require the low power, high speed, and secure devices. So here, how we are going to have this low power, high speed, and secure devices? This can be obtained only when you make use of the devices where we are using the transistors at reduced length of the channel. So how we can make use of the transistors at reduced length of the channel, that we are going to be our discussion. So in the IoT field also, whatever the devices which are connecting the wireless one, in that also we require the devices which is going to have high secure, low power, and high speed. So in this one, by using the transistor circuits in these devices, whether in the devices, whatever the CPU, memory, any circuits which you are going to use, all the circuits are made up of transistors, and those transistors has to be operated at reduced length of the channel. So which whatever the MOSFET which were used earlier at the large length of the channel, that failed to provide the low power, high speed, and security which is required for the latest technology. To overcome that, they have gone for the emerging devices, that is nothing but a FinFET and a gate all around FET. So here in this one, how these devices failed and how it is going to be overcome, that we are going to discuss. Before discussing that, we have to know about the Moore's law. As everyone know that from 1972 till date and till the 2030 also, the number of transistor, whatever the circuits are used in the form of IC, that circuits should have the transistor double of the previous one. So why the Muri has stated that? So here, when they have used a MOSFET or longer length of the channel, once they have increased the number of transistors for every new IC, they have seen that it is going to have low power, high speed, and secure devices were there. But once the length of the channel is reduced below 15 nanometer, they had Moore's law is going to be have the opposite operations. That is, it is going to be fail now. So here, how to overcome that? By not sticking to the Moore's law, comes to the emerging nano devices. So when we go for structure of, before getting to the emerging devices, we have to have some knowledge of the structure of the MOSFET. So whenever we go to the MOSFET, as you know, as everyone know, when you go for a NMOSFET, we are going to take a substrate, and source and drain are doped of N type, and the oxide is placed over this one, and gate is placed over this one, whatever the gate, aluminum metal or whatever you are going to take. So here in this one, when this length of the channel between source and drain, we are going to have the channel one, which is going to allow the carriers to move from source to drain when we give certain gate source voltage or drain source voltage. So as long as this length of the channel is long, that is below 50 nanometer or 20 nanometer, this is obeying good behavior according to the Moore's. So once the length of the channel is below 20 nanometer, this is going to be failed. That means as Muri said that for every new IC, the number of transistors has to be double of the previous one. How the number of transistors will be increased? Whenever we take a devices, the devices size is a portable means, then we can take that will be the good one. So how you can get the portable devices when we reduce the size of transistors which we are using in our circuits? How the transistor reduce size can be reduced? Whenever with the length and the width of the channel or the source and drain dimensions is varied, or oxide thickness is varied, reduced, then we can reduce the size of the transistor. When the size of the transistor is reduced, then device length of the channel is reduced, they have got low power, high speed, and good security. But when the length of the channel is below 20 nanometer, this one, it was behaving opposite behavior. Okay. So here in this one, you can see the when the length of the channel is this, it was behaving good. Moore's law, it is obeying Moore's law. But when it is length is reduced, it is behaving in the opposite way. So here we can see that around in the structure of the MOSFET, a depletion region will be formed across the source and drain. So due to this depletion region, as we increase the drain source voltage, there will be more potential barrier across the source. So because of the more potential barrier, or some problems are obtained. So that problems we are calling as short channel effects. So because at reduced length of the channel where it is failing the Moore's law, we can see at the length of the channel below 20 nanometer, these undesirable features are obtained in our MOSFET. Those are nothing but drain-induced barrier lowering, punch-through, velocity saturation, hot carrier effect, impact ionization, and mobility degradation. As we know, drain-induced barrier lowering is nothing but as we increase uh, as we increase the drain source voltage. So as we increase the drain source voltage, whatever the drain source voltage we are using, the potential barrier across the source and channel region, it is going to be whatever it is going to be decreased. So because of that what is going to happen? The threshold voltage of the device is going to be reduced, and because of that leakage current is going to be increased. So with the increase of drain source voltage and reducing the potential barrier across source and channel, which is reducing the threshold voltage and increasing the leakage current, that is called the DIBL effect. So leakage current should be less any devices which we are using. So this is the undesirable effect which is produced in the short channel MOSFET. Punch through, even in the punch through is another undesirable effect which we are going to have. So here, as the length of the channel reduces, the depletion region around the source and drain at one situation they will collide. When they collide, a large amount of current is going to be flown from source to drain without the dependency of gate source voltage. So here that one will result more leakage current. So even this should not be there. So velocity saturation means at a high electrical field, the mobility of charge carrier reaches saturation level, and it will not increase furthermore. Even this is going to be very bad undesirable effect. And one more is nothing but hot carrier effect. At high electrical field, what is going to happen? Whatever the charge carriers are there, that charge carriers, that is here in this one, here, because it is a N type MOSFET. So here whatever the electrons are there, for a given positive gate source voltage, it will go into attract at the gate terminal. So at a high electrical field, the charge carriers is going to be trapped under the oxide region. So this the charge carriers trapped at oxide region at a high electrical field is again is going to degrade our device performance, that is increasing leakage currents or increasing the power. So this is again an undesirable effect which is produced at low short channel length of MOSFET. Even at a high electronic field, this charge carriers is going to create more electron and hole pair. That is called as impact ionization, which is going to increase the power and increase the leakage current. So all these problems which is present, a short channel length of the MOSFET has to be addressed whenever we want to use a transistor at a length of the channel below 20 nanometer. And whatever the MOSFET which we were using and in which is present in our syllabus, because as we know our syllabus is 30 years back, we have to upgrade ourselves. So here in this one, this MOSFET, existing MOSFET cannot be used because these problems are present. So to overcome that, what they have done, so here one more problem is also present, that is nothing but subthreshold swing or subthreshold slope. This is nothing but it is the slope of VGS and the logarithmic of ID which you are going to tell. It tells how much drain current flows for the given VGS. This should also be low as the length of the channel is going to be reduced. Even DIBL should be less as long as length of the channel is reduced. So here in this one, as we discussed just now, for long channel MOSFET, as the length of the channel at 20 about 20 nanometer, threshold voltage is not going to be changed. It is going to remain same according to the manufacturing fabrication. Subthreshold slope also going to remain same. and even on and off current is going to be increased or decreased with a proportion of the drain source voltage is given. But when we go for short channel devices, here we can see that if a drain voltage is increased, uh, here in this one has a drain voltage is increasing. So here graph is showing gate source voltage versus drain current for the given drain voltage. If the drain voltage is increased, even the drain current is going to all be increased 100 times. But if you take, this is the on current and this is the off current. So here off current already we know that off current is increased more than on current. So off current is increasing means what? Leakage currents are more. So this should not be there. Whenever we reduce the length of the channel, off current should be reduced as much as possible. So even in the short channel, the threshold voltage is going to be changed. Earlier here it was there, and some again it earlier it was there, and again it is got changed some other value. Threshold voltage variation should not be there. This is a problem which we are going to have. And here in the, if you go for semiconductor industry market, they have Intel and TSMC company has announced that they are going to use this tri-gate uh, FinFET below 22 nanometer technology, and it is going to estimate the industry growth some $32.7 billion. So that's why a whole world is a back of semiconductor industry, which is going to provide a lot of opportunities for the country, every country growth. So here we can see that when we go for the normal MOSFET, in the normal MOSFET we have seen a single gate. Even in the MOSFET we can have two gate, three gate, but problems as will be present if you go for in n number of gates also. Here we can see a single gate and double gate MOSFET. So here we can see the graph, length of the channel and the DIBL, that is drain induced barrier lowering and subthreshold slope. So here we can see that here this this is showing, this is single gate one red color, and this is one is nothing but the double gate. So here subthreshold slope for the double gate, that is two gates if you used in the MOSFET, it got reduced. Even DABL got reduced. If these two are less means leakage currents are less and power is less. So if we increase the number of gates, if any transistor, it is going to show good performance, that is low power and leakage less, and even the speed is going to be more. So according to the ITRS, before 2016, worldwide one organization is there. That is nothing but ITRS, International Technology Road Semiconductor. Now after 2016, it is called as IRDS. That is International Roadmap for Devices and Systems. So this is the organization which will tell for the researchers and engineers what type of devices they have to use and how much should be the parameters of the device which they have to make use when they are making the circuits with those devices and the circuits which they are using. So if we see here logic device, according to the suggestion 2017 also they are making that, till 19 FinFET was used. So here this is one type of FinFET, fully depleted SOI, and this is a lateral gate around FinFET they are going to use. Either they can make use of FinFET or lateral gate all around FET. Here also 21 also either lateral gate or vertical. What are those? In the next session I am going to tell. Once we see the structures and operation, then you will understand what it is. But which year till what devices they are going to suggest, that just I am showing the table which is given by this organization worldwide. And 2024 they have said we have to use a vertical gate all around FET by this multi 3D integration technology. And here already till 30 vertical gate around with the multi integrated circuit 3D technology we have to make use. So here in all this one, either from 2015 to 30, FinFET and gate around FET they are using in the circuits making the semiconductor industry for getting the enhancements. None of them they are using the MOSFET, isn't it? So here, and the length of the channel they are from 15 to till 30, they have made use of from 16 nanometer to now the we are in 2026 till to 27, 3 nanometer, 2.5 nanometer, gate all around FET transistor they are using. And in this one, in the once we go for 30, it will be 2 to 2.5. To make the length of the channel of that much less, how much the design concepts we have to use, how with that one taking into consideration fabrication techniques and design concepts, behavior and lowering all the short channel effects which I said, we have to get the low power and high speed devices. So here my research which I have done is based on the 7 nanometer, from 20 nanometer to 7 nanometer FinFET I have taken. But future, whoever want to do the good research or want to get papers in the good journals, they have to publish the papers based on the FinFET circuits or vertical gate all around FETs, and whatever circuits they are making with these devices, they have to make these circuits making use of TCAD, Centauros TCAD or Visual TCAD, using those one, and that should be validation should be there. So whatever we are doing, validation means simulated work should be compared with the experimental work, which the earlier literature work which is done by the other authors. If we do in the good journals, we are definitely will get the papers based on this one. And the supply voltage which they have suggested is from 0.8 to 0.4. So this one, taking this table, we have to design our circuits. So here, before getting the FinFET one equations, so how this FinFET is going to be varied with the MOSFET? As we know that MOSFET, in the substrate only we are making the source and drain. Over that we are forming the gate material. So here, whenever we go for this, is one kind of bulk FinFET. So here in this one, this is the substrate one which they have taken from the substrate only a part. So if you take a N FinFET, a P substrate will be taken. In this one, a part of the substrate is taken as a to form the source and drain material, that is P type material only. Between source and drain, they are going to make use of channel region. Whatever the source, drain, and channel is there, that is called as a fin. So over this fin, they are going to place some oxide. After placing the oxide, they are going to place the gate material. Okay. So here in this one, you can see how many gates are there. This is a front, back, and top. So here when you go for the FinFET, only 3 gates will be there, which is placed over your channel. Okay. So here in this one, from substrate to here, this is a pin height, and this is whatever the channel length is there, almost that will be equal to the gate length. Yellow color which you are seeing is nothing but oxide. They can make use of silicon dioxide, hafnium oxide, or some combination also they are taking now, with the by varying the oxide material, fin height, oxide thickness, we can get a good performance in the circuit. So here in the real time industry, where this FinFET is used. In 2012, Intel company has made one processor in the mobile SoC industry, where they have used this 22 nanometer FinFET in the SoC. And in the Samsung also, they have made use of 40 nanometer in their SoC Exynos in making the smartphones. TSMC also made use of 10 nanometer FinFET in their SoC of 7420. So in the practical semiconductor industry, they have made use of this FinFET devices. Now they are using nanowire FET and gate all-around FET is now in the research. So this is the main. First in the 1990, one author published a paper which he has made, that FinFET they have shown here. Here you can see that whatever they have done, that is called as a depleted lead channel transistor, and they have taken the substrate. This is also bulk type of FinFET. Over that, from the substrate only, they have taken the material, P-type semiconductor material. From that, they are going to form the source, drain, and gate. And over the gate oxide is placed. After that oxide, over that a gate material is placed, wrapping the this channel region. So in another, in 2086, that was the bulk FinFET. This is the SY FinFET. So in the SY FinFET, from the substrate only, they don't take the source and drain and channel material. they will take separate over the substrate. They are going to place the oxide over that. They will take n type material. If you take a n MOSFET, they will take n type material, and from the n type, one end will be the source and drain, and over that oxide is placed. Next, gate material is wrapped here. So here in the one paper publication 2022, they have shown how much height of the pin and thickness of the pin we have to take so that to get a good performance in the circuit. Height of the pin should always be more than the thickness of the pin which we are going to take. So these are the two types of FinFET which you are going to have, which I have shown earlier. First FinFET is nothing but bulk FinFET, from where we got it, the source and drain material from the substrate which they have taken. SOI FinFET means first they will take the substrate, over that oxide is placed, either silicon dioxide or hafnium oxide. Now they are taking some advanced material combination of oxide material also. Over that again, then if you are taking N MOSFET, N FinFET, SOI FinFET, n-type material is placed, which is going to form source and drain, and between source and drain we are going to have the channel material over the. After that, oxide is placed, yellow color which you can see. Next you are going to place the gate material is wrapped around this one. So what is the difference which you are going to have in SOI and bulk FinFET? In the SOI FinFET, as you have said, the height of the fin is less, bulk is parasitic capacitance. Here it is going to have more, it is going to have less. So this is about the this one. Apart from the bulk and SOI FinFET, we are going to have double gate FinFET. Only two gates can be used, or triple gate, which you have seen now: top, bottom, and front, back, and top. A pi gate means your gate will be wrapped as a pi shape. Omega FinFET, independent gate FinFET means whatever the two gates are there, separate voltages we are going to give. Short gate means two gates will be connected together to give a common voltage. Junctionless FinFET means whatever the source, drain, and channel is there, it is doped with the same amount. So here you can see the two type, which is which we formed in the Visual TCAD, where we formed using the structure, taking the materials. This is a two gate FinFET, and this is nothing but three gate. So front, back, and top. This is oxide source drain. Okay. So here this is a SOI FinFET. So current industry, how they have gone. First they used MOSFET. After that, bulk FinFET, which I discussed. After bulk FinFET, they have gone for the SOI FinFET, because they want the low power, low leakage, and high security, high speed. To get that one, they have gone for that. After in SOI FinFET, they have gone for the gate all around FET. Gate all around FET means instead of three gates, it is going to have four gates. Total around whatever the channel region is there. Here in the FinFET, you have seen only the front, back, top. When you go for gate all around FinFET, below also you are going to have gate material. When you go for that means it's all total. If you take our four fingers and with the other hand if you wrap totally, so that will be equal to your gate around FinFET. So here when we wrap the gate horizontally, it is called as the lateral gate all around FET. If you wrap the gate vertically, it is called as vertical gate all around FET. So here next I said they are going to take monolithic fabrication of ICs. That means different layers of circuit is made on the same substrate. So now the industry, now presently they are making gate all around a nanosheet transistors. What is this nanosheet transistor, that we'll see. So here Samsung has used using 3 nanometer gate all around FET. Intel gate all around FET. TSMC also 2 nanometer gate all around transistor they are going to use. So why they have gone from the FitFET to gate all around FET? Because to have the, as I told you, it is going to have lower leakage, low power, high speed at a length of the channel, 3 nanometer, and it is having better performance compared to your FinFET. So here we can see the major difference of the FinFET and gate all around FET. Here in this, when we go for structure wise, here gate is going to surround the channel only on three sides when you go for FinFET. When you go for gate all around FET, gate is going to completely surround on four sides. Channel, it can be vertical fin, here it whatever the channel is there, it can only be the in a vertical way they can put it. Here they can place either in horizontal or vertical frame, channel one, and they can make use the channel material between source and drain as a nano wire. When they make use of nano wire, the channel, it is called the nano wire FET. When they make use of nano sheets between source and drain, it is called a nano sheet FET. They make use of in rubber form, the channel material is called as a nano ribbon FET. All this comes under gate all around FET. Electrostatic control is good here. It is more good in your GAA. Short channel effects are reduced compared to your MOSFET. Here, short channel effects are still reduced compared to your FinFET. Leakage currents are very low. Drive current is more, and in this one, subthreshold spring is less here. DIBL is lesser compared to your FinFET. It should be low as the length of the channel is reduced. Power consumption is lesser. Scalability at 3 nanometer, 2 nanometer, still lesser you can use here. Here this is used effectively till 5 nanometer. Fabrication is more. Here cost is going to be more when you go for GA FET. So here one, how the performance of the circuit is going to be varied when we change the design parameters when you go for your FinFET. So here we can see that at the exact in the one paper published, fin height whatever they have used in this one. So as they decrease the uh, height of the fin, and increase the thickness of the fin, what is going to happen? The threshold voltage is decreasing. So by changing the height of the fin dimensions and the thickness of the fin, we can vary the threshold. We can change the threshold voltage. If the threshold voltage is less, means it is good. At lesser supply voltage, we are going to have lesser threshold voltage, and the device will be on soon. Power will be reduced. So another one which we can see that depending on gate length is nothing but length of the channel which we are using. So if the length of the channel is reduced, what is going to happen? The delay of your whatever the device which you are going to be is reduced. If the device reduced, delay is less, the circuit's delay will be less, and the device whatever the gadget which you are using, their delay also will be good. So here in this one, if we take N FinFET and this dark this line is signifying for the N FinFET, and this is going to signify for the P FinFET. Okay, so here in this one, and this is nothing but ITRS suggested in 2001. So here in this one, whatever they are having, almost they are going to have the same for that length of the channel. So in 2001, length of the channel, they have ITRS suggested 10 nanometer. So at 10 nanometer, so as the length of the channel is reduced, what we have seen, the gate delay is reduced. Delay is reduced means speed of the device or circuit is going to be increased. So here this N FinFET or P FinFET is going to have almost the same value which they have. This is the fabricated one, and they are comparing with the suggested ITRS one. So if they almost they have got the fabricated one equal to that whatever suggested, and these are the characteristics of your P FinFET and N FinFET and P FinFET. This is equal to that of whatever we study for enhancement, N MOSFET and P MOSFET. As we increase the drain source voltage for increased gate source voltage, the drain current is going to be increased for. So here we can see how the parameters they are going to take for design of any circuit in 2018 in IEEE transaction one paper. For different length of the channel, they have designed a circuits based on some security circuits. They have taken the length of the channel 16 nanometer to 17 nanometer, and they have seen and they have taken the gate length of these values, height of the fin width, oxide thickness, and supply voltage. So we can observe that as the length of the channel is increasing, what are the dimensions of your FinFET is there? That is gate length, fin height, fin width, oxide thickness, and even supply voltage is reducing. So all if you reduce, we are going to have the desirable effect of whatever we want for the device to be worked on. So here they have made for one circuit, adiabatic logic circuit they have taken. Adiabatic logic they have used for implementing the AND gate. For different combination of the AND gate, they have taken the leakage currents with the change of technology node. Whenever in the research or the industry they say technology node, it represents whatever the length of the channel which we are using in that particular transistor. With the previous work, and this is the length of the channel of the FinFET from 2 nanometer to 7 nanometer. So they have observed that as the length of the channel for every combination they have used, the leakage current power is going to be reduced. So again, this we can see that in the MOSFET and FinFET they have used. So whenever we do any comparison, it is better that if you take a MOSFET 22 nanometer, FinFET you can take, also you can have to take 22 nanometer or between, plus or minus here and there. So if you see here in this one, in for MOSFET 22 nanometer and FinFET 20 nanometer, the delay of the MOSFET which they have used is got is 1.5. Okay. And here they have got some 0.16. That means the delay with your FinFET experimentally they have done. So here in this one, the FinFET experiment, they got a delay less. So with this one, with the experimental simulated results, so this all this one, but simulated again fabricated should be compared that is the effective. So as a academician, we are going to have the exposure with the simulated one only, and practically also experimental industry people have done, and they have got good results with this device. So next comes our nanowire fit. So whenever we have gone for this nanowire fit, so already I told you they are this nanowire fit, four in the four where four gates are surrounded around our whatever the channel is there. So here this is our source and drain. Between source and drain we are going to have a channel region, and the gate is going to be wrapped around whatever the channel which you are going to take. So your whatever is the blue color which you are seeing is nothing but your gate one, and here this is nothing but insulator oxide, and green color which you are seeing nothing but a source and drain and channel will be there in between that. So here this is the circular nanowire fit, and whatever the channel which they have taken source drain and between channel they have taken rectangular type. So by changing the shape of your the channel part also is going to enhance change the performance of the circuit. So here in this one, whenever you this is about your nanowire fit, and so here in this one current equation for the whatever the FinFET is there, every device is going to have some, as we know for MOSFET, at the saturation region or cutoff region, it is going to have different behavior. Based on that behavior, we are going to have some mathematical equations. Using the mathematical equation only, we can do the modeling. What do you mean by modeling of devices? Means with the equations behave depending upon the operation behavior of the circuit, how that circuit is going to work. That is expressed in terms of some mathematical equations. The using those mathematical equations, we are going to check how ion current, I of current, threshold voltage, and uh, DIBL subthreshold slope is going to have for the circuit. Okay, so here in this one, this is the one your FinFET current equation. So here this is that is VDS lesser than saturation one. Drain current of your FinFET is depend upon the mobility, oxide capacitance, and width of the channel, gate source voltage, threshold voltage, and drain source voltage. Similarly, in the saturation region, it is also depend upon the width. If you vary the width of the channel or mobility of the charge carriers, width of the channel, and whatever the effective length of the channel, that is nothing channel length modulation parameter. By varying that, we can change the current. So here width of your channel, width of the whatever the fin is there for your fin fed, it should be equal to of this value which is given by the analytical modeling researchers. That is nothing but 2 into height of the fin plus width of the fin. So here this is the effective for tri-gate. This is the effective width, that means total width, considering height of the fin and width of the fin. Threshold voltage also will be varied depending upon your DIBL effect and also the length of the channel and the drain source voltage. So here we can see that as a nanowire FET, by changing the shape of the nanowire, that is from rectangular to the cylindrical. The here we have taken the graph based on the length of the channel and the on current of the device which you are going to take. As what is happening here, as the length of the channel is reduced, as the length of the channel whatever is there is reduced, whatever the on current is here they have shown the on current. Here green color is showing that our nanowire, whatever the GA is there, it is in the cylindrical shape. Blue color it is showing the rectangular, and red color it is showing the FinFET device, and last black one it is showing the double gate MOSFET. So here in this one, at this whichever the length of the channel they have taken, the double gate MOSFET is having less on current compared to your FinFET, and in this compared to the FinFET, GA is having more current, isn't it? So here in this one, this cylindrical shape one, GA is having more current uh, compared to your rectangular one. That means shape of the whatever the channel and source drain which we are using, even that is going to affect the on current. Or any device if on current is more, that is a good one. It is going to lead to the less leakage. So again, you can see in one paper published in 2017, uh, uh, they have shown they have used both the combination of silicon and germanium material, which is going to act like a channel region in the FinFET. And what they have done, they have reduced the and the x-axis they have taken the gate source voltage and the drain current as they reduce the length of the channel. So what is happened as they reduce the length of the channel? So here in this one, they have reduced the length of the channel from 20 nanometer to 5 nanometer. So as they reduce the length of the channel, here whatever the current is there, your drain current, here the drain current is got increased. This is nothing but here whatever we have is nothing but here high of current which is going to be increased. And here as they reduce the length of the channel, whatever the transconductance is there, transconductor parameter is also going to be reduced. So here in this one, as transconductor is reduced, what is going to happen? The speed of circuit is reduced. So this is a problem they have identified. So that they at the reduced length of the channel, whatever the decreased speed there, they have to increase. So instead of one fin, we can make use of more fins also. So here you can see the n number of fins made on the substrate. Over that, oxide is placed, and over that gate is wrapped around this. N number of the n number of fins if they are increased also, what is going to have performance is going to be enhanced. So here in one published paper they have shown over that gate is placed, and this is a three-sided pin pit. And here now you can see that this is nothing but a nanowire FET. So in the nanowire FET, what I told you, it is also one kind of GA. GA is nothing but gate all around FET. So in the gate all around FET, how when we can call the GA FET as a nanowire FET. So here, whenever between source and drain, whatever the channel region is there, if this channel region is in the form of nanowires, so the, then it is called as nanowire FET. Instead of nanowire FET, if they are in the sheet form, then it is called a nano sheet FET. Okay. So here we can see this and Samsung which they have used. This is nothing but a nano wires between source and drain channel region made of nanowires. So here n number of you can see this source and n number of source and drains are there, and n number of channel. That is nothing but whatever the channel region is there. That is a more than one fin is used here. So instead of the wire, if it is in the sheet form, then it is called as nano sheet FET. So here in this one MBC FET, that is a multi-bridge channel FET. That means in the multi-bridge channel means n number of fins are used, and they are all the circuits made up of this device is fabricated on a single substrate. So here we can see how the ion current is going to be varied with germanium nanowire FET and the silicon nanowire FET. So here if we go for germanium nanowire FET and silicon nanowire FET, here the current it is showing which one germanium nanowire FET is having more current value compared to the silicon nanowire FET. What is the germanium nanowire FET? This germanium nanowire FET is nothing but whatever the channel region which we are used, the nanowire form that is made up of germanium. Here it is made up of silicon. And here we can see my paper, one published one, which I have done with the FinFET and nanowire FET. Here we can see that I have used 8 nanometer and 7 nanometer nanowire FETs. Here I made use of some codes, and using those codes behavior, using this pin files in the circuits, I got these results. So compared to the same 8 nanometer, nanowire FET is having less high of current. And here with the same, with if you go for 7 nanometer also, nanowire FET is going to have less compared to your FinFET. And in this one, if you see 20 nanometer FinFET and 8 nanometer FinFET, this 8 nanometer FinFET is having less IOF compared to your 20 nanometer FinFET. Next is ion. Compared to your nanowire FET and FinFET, this nanowire FET, in my result I got FinFET has more ion compared to this, but IOF is less. That is good. Power dissipation, when we compare FinFET to nanowire FET, this power dissipation is value is very less in your nanowire FET. So these are the values which we got with the circuits which we have made using FinFET and GAA at a length of the channel 8 nanometer, 20 nanometer. DIBL, if you see, compared to your FinFET and nanowire FET, the GAA is going to have less DIBL. That is a good one. That means threshold voltage change will not be there whenever their potential barrier is reduced. And here I of current it is going to have here also when we go for compared to GA and FinFET, GA is having less I of current. I of current less means the leakage currents will be less in the device, and behavior low power it is going to have. Ion current if we take, FinFET is having more ion, even we got this. Static power dissipation it is going to have very less. As we know, static power is nothing but power consumed the circuit when inputs are not changed. Ion and IOF ratio for a GAF it is a good one. So these are the different dimensions which we have used for the FinFET and GAA. LG reference, that is the length of the channel. We have used 20 and 17 or 8. This is nothing but height of whatever the channel is there is used UOT, that is effective oxide thickness. As the length of the channel is reduced. If you take a FinFET 20 nanometer and FinFET 8 nanometer, here oxide thickness for 20 nanometer we have used 1 nanometer. Here we have used zero point 0.4 nanometer. That means as the length of the channel reduces, the oxide thickness which we are using in the device making, even that should be less so that it is going to have less leakage. Okay. And in this one, height of the pin also, if you see, height of the whatever the channel we are taking, even that should be reduced when we go for reduced length of the channel. So even if you go for GA also, they have reduced whatever the height of the channel is there, oxide thickness is there, that they have reduced. And width of the channel also they have reduced. These are doping which is given for the channel source and drain value. Supply voltage, as the length of the channel reduces, supply voltage also going to be reduced. So this is another one published in IEEE transaction of and paper, FinFET and nanowire FET. and they have used different modeling files to get the simulation of the files. If I take this one, FinFET, this is the ion current and this is the I of current which you see. So here in this one, if we take this, FinFET is having more ion compared to nanowire FET. But I of, if you see, I of nanowire is less compared to your FinFET. So if I of is less, that device behavior is good one. So next we'll get into reliability analysis of high performance FinFET based circuit. Till now, with the devices, any doubt? Hello? If we understand the device's behavior, then only you can understand the applications which I am going to discuss. Hello? Can anyone? Any doubt? Shall I continue? Next
Yes, ma'am,
topic?
continue.
Okay. So next one is nothing but reliability of high performance FinFET based circuits. So here in this one, I have made use of some circuits. Those are nothing but domino logic circuits and multiplied circuit and SRAM circuits for the which will be used in the CPUs and SOCs for performance enhancement in the devices of which we are going to make you in the AI, and another one is nothing but IoT. Okay, so here reliability means what? So here whenever the supply voltage changes, main performance is nothing but threshold voltage and your power, speed, that should not be varied. So even if the supply voltage is varied or temperature is varied, they should not be varied. It should increased. So here, to overcome that, we need to analyze. The major task for the researcher is nothing but how to control the reliability issues which is present in the nano device transistors. So whenever we get into the reliability issues, we should know that is nothing but power dissipation. So here, whenever we go for in electronics, any circuit we take. So every circuit is going need to have important consideration is power dissipation. Now we are hearing about AI technology, IoT. These all are present in the 500 years back only. But earlier, whatever this AI technology and IoT, they are not able to implement it, but now they are able to implement it. So what is the major reason of implementation of that? The major implementation of that is nothing but whatever this AI technology and IoT robotics are working, everything should have work on our hardware circuits, and those hardware circuits are made up of devices that is nothing but transistors. So if these transistors has low power and high speed, then only all this algorithm is going to work effectively, which technology should be meant for. Earlier, low power devices and high speed circuits were not there. Because of the availability of now, these low power circuits, low power devices like your FinFET and nanowire FET, now this technology implementation is done. Now, even below for 1 nanometer, they have seen that even these devices are going to be filled. That's why they are going for quantum mechanics. So in the quantum mechanics, if you see, they are going to produce a novel devices, novel transistors. Other than FinFET and nanowire FET, maybe till 2035 like that. After that, world will be back of quantum transistors. Okay, entire behavior of transistors will be changed based on the quantum mechanics. So here in this, whenever whichever transistors are present, the main concept is nothing but power dissipation. So as we know that in the power, there are two types of power dissipations are present: dynamic power dissipation and static power dissipation. Overall power dissipation in any circuit is given by static, dynamic, and short circuit power dissipation. So whenever we get into the um, dynamic dynamic power dissipation, there are three types are there. One is nothing but switching power dissipation, short circuit power dissipation, glitching. Static power dissipation comes under your leakage power dissipation. So here in this one, whenever you go for analysis of using the devices making the circuits, separately we have to analyze dynamic power dissipation, short circuit power dissipation, and overall power dissipation, what is it is going to have, and leakage currents, how it is going to affect it, and the delay of the circuits. This analysis should be there. So whenever we go for what is a dynamic power dissipation, so as we know, the dynamic power dissipation of any circuit is nothing but it is the power dissipated in the circuit during charging and discharging of the capacitance present in the circuit. So short circuit means the whenever the transistors are there during the on condition of when you go for CMOS circuit, both when PMOS and NMOS is on, we consider the power dissipation when either of them is on, either P or N. So when we short in the short circuit power dissipation, that the power dissipation is considered when both are in on condition. At that condition, whatever the current is flowing from VDD to ground, that power dissipation, the current flown from VDD to ground during the on condition of both transistors, that power dissipation we call it as a short circuit power dissipation. Static power dissipation is nothing but a leakage current power dissipation. Here in this one, the power dissipated in the circuit when the inputs are not changed, that power dissipation we call it as, that is steady logic 1 or logic 0, that power dissipation we call it as a static power dissipation. So here in this one, static power dissipation, as we know, it is given by supply voltage into the leakage currents which is flowing in this one, and switching power dissipation is given by the charging and discharging capacitance and switching activity which is produced in your circuit. Short circuit power dissipation is given by supply voltage and the short circuit current given by this one. So all these circuits analysis, first on the simulators, either with the cadence or synopsis, we can make use. When you are going for the device level modeling or device level make circuits, we have to make use of visual T code or Centaurus T code. Okay. So now I think in the central government also has given one option of chip to startup. If we all colleges register in that one, nearly all the whatever the software tools are there, which is not possible for us to work or purchase, they are giving the free of cost. So that facility we can have, and we can do good research on the advanced devices which we are going to have. So here, as we know that dynamic power dissipation, if the capacitance changes or supply voltage changes, if more supply voltage is there, dynamic power dissipation is going to be more. The capacitance is more, dynamic power is also going to be more. Switching activity more means dynamic power is also more. So if you reduce any one of this one, dynamic power dissipation of that particular circuit or device is going to be reduced. So when we go for leakage currents in your device, that is FinFET and nanoFET, leakage currents will depend upon the oxide capacitance. If it is less, the leakage current is going to be more. If the length of the channel is less, we are seeing that the leakage currents are more. That we have to reduce by making the entire design fabrication of that transistor change. Next, threshold voltage, if it is more, leakage currents are more. Drain source voltage and gate source voltage are more, means this is going to be more. So by varying these parameter values, we can get the suitable leakage currents which we want to make has a low leakage current device and low power device. So here, whenever we go for any device, not only FinFET, we have to consider this one: environmental effect, voltage variation, process variation means fabrication. Whatever the techniques which we are using, by changing that, that is temperature and supply voltages. Whenever we consider all this, we can get the good device. So in this one, analysis should be is done to get the low power and high speed. Next, in the applications, we are going to analyze reliability issues for the high performance domino logic circuits from 20 nanometer to 7 nanometer. Next, multiplier circuits, static and dynamic power dissipation from 20 nanometer to 7 nanometer, and leakage powers for SRAM circuit of 7 nanometer technology node. So how we generally start we have started for FinFET and nanowire FET, the working of these application circuits. First, literature survey is done, what the previous have done, and every device which have worked, those devices I have worked making use of BSIM, CMG, PTM files. BSIM, CMG, PTM files already you know, Berkeley simulated common multi-gate predictive technology model files. That is available in the Arizona State University. From that you can download. By taking that, whichever the circuit enhancement we want, by changing some parameter values in the which they have given, we can get the performance, good performance of the circuit. Either using the cadence, or you can make use of synopsis, mental graphics, even now Semica also you can do. Circuit level simulation only you can do with the mental graphics, these devices, and uh, cadence, mental graphics and synopsis. When you want to the device level and the circuits only limited to some 10 transistors, you can go for centerless TCAD. More, with the visual TCAD also more than till 50 transistors circuit making that device also you can make. But with the device level circuit making, centerless TCAD is a standard industrial tool. And after making the simulation, we have to analyze the reliability analysis. So these are the literature survey previously done before doing the uh, issues, studying the issues of the circuit. In 2006, one author they have done the different multipliers implementing on the Spartan 6 FPGA, and they have studied the performance, that is their power, speed, and area on the Spartan 6 FPGA. But once we study FPGA implementation performance is only prototype. Doesn't show the actual power and speed. Only it is gives an idea. So to make the idea actual practical fabricated type circuit, we have to analyze with the devices only. So I have made using this multiplier circuit using the FinFET files to show them the actual implementation to get the less power and high speed. Next in 2019, one more author they have done a multiplier Vedic multiplier using 32 nanometer FinFET to get the low power. So I have made instead of 32 they have used normal BSIM files. Here I have made use of BSIM CMG files. So here I have made use of instead of 32 they have made use of 7 nanometer. And in 2018, one more author using the adiabatic logic circuits, they have used from 20 nanometer, 7 nanometer FinFET files. They have analyzed the circuits, leakage powers and power. I have made use of, they have used normally, they also use normal files, BSIM files. Here I have used BSIM CMG file to get the still lesser power. And in 2009, they have made use of 180 nanometer CMOS multiplier. 180 nanometer means what? The length of the channel which they have used is nothing but 180 nanometer. So here to get the still lesser power, I have made use of 7 nanometer in my research. So in 2015, one author, Joseph White, he has made use of 7 nanometer and 14 nanometer files to get. They have used normal files, have used made some advanced BSIM CMG files to get the lesser power. 2017 also one multiplier they made Valastri and Vedic multiplier implemented on the Spartan 3 FPGA. So instead of FPGA, here I made use of an enhanced BZ multiplier using 7 nanometer. In one author in 2019, they made use of comparison of all the multipliers using Xilinx. Here we have used of FinFET. So here we can see that what is the how it is going to be varied with the temperature, whatever the circuits which we are going to have. So here I have made use of some domino logic circuits, different types of the domino logic circuits. So here we can see that as the temperature increases, okay. So as a temperature here, x-axis temperatures will be taken and y-axis power dissipation. And here as the temperature is increasing, what is happening? The power dissipation of whichever the domino logic circuit we have taken, that is increasing. So here my proposed one is nothing but a set reset logic, domino logic and high speed the cascade circuit, domino logic circuit that is having lesser power dissipation compared to the existing one, whatever is there. So here how this power dissipation is increasing with the increase of the temperature. That is the most important thing we have to discuss here. As the temperature is increasing, what is going to happen? The mobility of charge carriers is decreasing. So with that one thermal equivalent, one also the thermal equivalent voltage is increasing. So here in this one, it is, you can see that Vt is given by Kt by Q. So it is inversely proportional. So as a charge carriers, whatever you have, this if it is decreasing, Vt is going to be increased because of that leakage currents are increasing. So if leakage currents is increasing, what is going to happen? It is going to increase in the power dissipation. So as we increase the temperature in the operation of the FinFET device, this power dissipation whatever is getting increased. This is one problem. So this is a research problem. This we have identified. But when the new researcher is doing, what they have to do, whatever that was increasing, earlier it was increasing more value. We have made a novel circuit where it is got reduced power compared to the existing one. That is a research solution, isn't it? So this was increasing because of the leakage currents increase. How this leakage current is increasing? Because of the decrease in the mobility of charge carriers because of due to temperature rise. Next one comes how it is going to affect the delay. So here in the delay, whatever we have, as we increase the temperature, here it is observed the delay of whatever the is there. This is also delay is also increasing. So but they what are the proposed one is there, that is SRLC and HSCC. This is going to be decreased, isn't it? So here in this one, as we why it is increasing as the temperature is increasing, delay factor. So here they have seen that the threshold voltage drops with the increase of the temperature. So because of the dropping of the threshold voltage, it is increasing the leakage currents. Because of the increase in the leakage currents, what is going to happen? It is increasing the delay. Okay. So here in this way, temperature effect will be there, which is going to affect the power dissipation and delay of circuit, which is again dependent upon the mobility of charge carriers and threshold voltage. So next one is nothing but how the power dissipation is going to be varied with the supply voltage. So here whatever the power dissipation which we have, okay. So here in the, as we reduce the supply voltage, it is seen that power dissipation also got reduced. So as we know that P is equal to V into I. If V decreases, power also decreases. So in the FinFET domino circuits, which is used in our latest processor and SOCs, all these effects can be observed, and this will be useful feature which will be used in the making of the circuits. So here we can see the increase in supply voltage causing the increase in power dissipation because of the increase in threshold voltage and the leakage currents. So next comes how supply voltage is going to affect the delay. So here we can see that as supply voltage is increasing, the delay here it is going to be decreased. Power dissipation it was behaving opposite. As we decrease supply voltage, power dissipation was decreasing, but delay it is increasing. So why it is happening in this one? How was the reduced supply voltage? It is showing more value. So as we increase supply voltage, this this rising threshold voltage is going to reduce whatever the on current is there. Because of that, latency is going to be reduced. Because of that, we are going to have the reduced delay. So next which we are going to have is nothing but supply voltage. How supply at supply voltage and the delay in this one. So here at a threshold voltage of 0.01 volts. So here this is only one circuit. Here two were there. The results show the supply voltage decreases the delay for this circuit. Delay of the circuit is earlier you have seen that it is increased one. This is the problem. That actually the reduced delay we need to have. So how we can have the reduced delay? So here in this one, the reduced delay is another enhanced feature is done for that one. So the reduced delay, whatever it was having at the less supply voltage, now it was more delay was there, that was reduced. How it is reduced? So here in this one, how we got a reduced one. So the result shows that as supply voltage decreases, delay of circuit is also decreasing. So how it is going to decrease because of the whatever the VTH was more, that it is got, we made a reduce of VTH by changing the length of the width of the channel or height of the length of the channel or height of the pin or width of the pin or oxide pin, any one of the parameter if we change. Here the VTH is going to be changed because of the reduction of VTH. Whatever the increased delay was there, that got decreased. Next one is nothing but the multipliers. So in the multipliers, we are going to discuss one multiplier is nothing but add and shift multiplier, and another one is nothing but bypass BZ fat. Bypass direct feed adder. So here in this one, these two multipliers has taken and sample one. Already we know how multipliers is going to be worked. Here we have taken a multiplicator and multiplier of this value. So to do this one, it is taking approximately 8 cycles to get the product value, whatever we got it. The first one, and enhanced the next multiplier is this one. Earlier it got to 8, has taken 8 cycles. Now it is taking only 4 cycles to get the product value. So here in this one, for this one, whatever is there, I have analyzed for this multipliers. Uh, this dynamic power dissipation and the static power dissipation. Okay, so here in this, whatever this dynamic power dissipation and static power dissipation is there, so you can see that as the length of the channel is reduced, whatever the length of the channel is there, the dynamic power dissipation is what is happening here. Dynamic power dissipation got reduced. Okay, so here why we have reduced the, how it is going to reduce the dynamic power dissipation as the length of the channel is reduced. So here we at the length of the channel 20 nanometer we are going to use the supply voltage of 1.2 volts like that. Here whenever we go for 7 nanometer supply voltage we are going to take zero point 0.7 volts. Oxide thickness is going to change. Height of the fin is going to be changed. Width of the fin is going to be changed. Okay, so here in this one, by changing, because of the change of this, at reduced length of the channel, it is going to have less dynamic power dissipation. Already I discussed what is the dynamic power dissipation. So next one is nothing but this is as the multiplier size increases, that is 4 by 4 or 8 by 8 or 16 by 16. That is that those many number of bits for the given inputs are increased. The dynamic power dissipation is also going to increase. Next one is nothing but delay. So here in the delay we can see that uh, even the size of increases, the delay is going to be increased. And next comes here how with the technology node the delay is going to be changed. So here in this one, as the length of the channel is reduced for the multiplier using the FinFET, the delay got decreased here due to reduction of threshold voltages and the dimensions of your FinFET which we are used. So here we can see that is about the power and delay. That is separate dynamic power. Now we are going to discuss the static power dissipation. So static power dissipation is nothing but, as we know that it is the power dissipated in the circuit when the inputs are not changed in this one. So inputs are not changed means although as if it off state. Whenever in the circuit device is in off state, off current is going to flow. Off current is nothing but leakage currents. So what are the power which is going to be given out, power dissipated due to leakage currents, that is nothing but your static power dissipation. So as the length of the channel is reduced, we are going to see that static power dissipation is going to be more in the FinFET area. Circuits made up of FinFET. So this is the one major problem. How we have to the research, we can provide whoever is doing next research, they can check out that how they are going to reduce the static power dissipation, which is present at this reduced length of the channel. So next comes is nothing but the SRAM circuits. So in the SRAM circuits, before the SRAM circuits, we can see that different domino logics and the power dissipation produced. Okay, so here we can see that 32 nanometer CMOS, the power dissipated, overall power dissipation. This is 0.74 microwatt. It is got same instead of MOSFET. If we make use of FinFET, it is having some 0.52 microwatt. That means experimentally they have seen this. It is going to have less. So which we have suggested for same length of the channels. 7 nanometer and novel circuits we have made where it is going to have less power compared to the existing one. So earlier CMFD was there, domino logic circuit. Hmm. 32 nanometer they have used. Here we have made use 7 nanometer. Even this was there. HSCD was there. 32 nanometer. CMOS was there. We have made use of 7 nanometer. We got the less power compared to the earlier one. And even this is having less compared to all. So when we go for comparison of FinFET based domino logic circuits at temperature only at 15 degrees, these are the different values. Any circuit if you make, we need to with that device, the circuits which you are making, we have to find out these parameters: delay, power dissipation, power delay product, area. Area is obtained by layouts which you are going to draw for that circuit, and energy delay product is nothing but delay and the power delay and the PDP of circuit which we are going to have. Okay. So here in this, which we for different homology circuit for the FinFET we have found, and this is for the multipliers at different technology nodes which we have done compared to MOSFET and FinFET. So here in this one, earlier authors they have used 130 micrometer MOSFET transistor for this multiplier, and so here in this one, and Vedic multiplier earlier they have used 7 nanometer FinFET, and they got 175. Now which we are used 7 nanometer, we got only 10. That means lesser we got. Earlier they have used 130 nanometer, and now 7 nanometer we got this 7.7. So array multiplier they have used. Okay, so here in this one with the designed or earlier with the 130 nanometer they got 10, with the 7 nanometer we got 2.7. That means it is a reduced one. And similarly conventional earlier 130 nanometer they got 10, uh, uh, here we got for the FinFET we got 2.7. So compared to earlier 130 nanometers MOSFET, FinFET multipliers using this device we got the lesser one. Next in the SRAM, leakage power. So compared to MOSFET, FinFET is going to have less leakage power. So with the MOSFET it was having 793 nanowatt. Here it is having some 1.98 nanowatt. Here it is having some 2086 nanowatts. Here it is having 1.6. How it is going to have the less leakage? So, what you have studied now, how will be the structures by varying what you are going to have, how you are going to enhance the speed and the delay. So, what is making the FinFET to behave and our gate all around FET is going to behave in such a good manner? Means mainly because of the gate control. The gate control, 4 gates or 3 gates are controlling the channel in a 3 or 4 direction effectively. Because of these reasons we are having the good behavior. So conclusion is nanowire FETs and FinFETs is going to have going to be the semiconductor revolution, replacing the MOSFETs, which is used below 20 nanometer, and this FinFET and nanowire FETs are going to have uh, backbone for SOC industry at low cost, and it is going to increase the revenue of every country. And the TSMC is making use to reduce the delay and leakage currents. They are doing a lot of research on that, and here in this one we have done is nothing but a simulated one. If fabrication it one is done and used in the SOCs, future coming SOCs, it is going to have the mm, drastic change in the one which we are going to have. So next I will show you one example of some in biomedical applications, where one amplifier used and how you can change it, how the whatever the simulated one which you have done, these simulated files have done using bsim files, how these bsim files is going to be look spice files, and how you can change the spice files and enhance the whatever the parameters are there. So this is all the published work which I have done in SCI paper, electronics, reliability analysis of input-based circuit, which I discussed now. So they have made use of SOI FinFET-based instrumentation amplifier for medical applications. What does this SOI represent, sir? Can anyone tell? Hello? Can anyone give the answer?
Yes, madam.
SOI. We discussed the classification of FinFET. No, so one they have used in the for biomedical applications for instrumentation amplifier. SOI FinFET. So as I discussed, basically in the 2017 they have used a silicon on insulator FinFET. Okay. So here in this one they have made use of an instrumentation amplifier. So we using the in the TCAD or Visual TCAD they have made this FinFET using some coding, and then what is the material they have used here? They have used as a substrate some silicon material, and they have made use of oxide, whatever the oxide they have used. This is below is a this is the substrate. P-type material, and they have used the oxide, silicon dioxide. Over that, they have made use of some. This one is nothing but ophium oxide. Both they have used. That is the insulator. Over that, they have made use of source and drain material. Source and drain is made up of some N-type material. Between the source and drain, you can see this is a channel region. So whatever this is, all this is nothing they have done in the writing the depending upon the dimensions and the behavior of that device, FinFET device, using the equations. They are that principal operation they are made use to build this structure. So materialistic form already inbuilt materials will be there in the Visual TCAD and Central TCAD. Using those dimensions, and we can make the this device. And in this one, over the oxide, they have made use of the gate, isn't it? So this is the height of the pin which they have used. So here in this is a simulated one. And in this one, for this amplifier, they have found this parameter values, transconductors, subthreshold slope, this is conductance, output resistance, voltage gain, this is frequency value, cutoff frequency value, how much it should be there, they have found. So here in this, for this instrumentation amplifier is used in the biomedical applications. So this is the circuit they have used. Whatever the op amps they have used here, those op amps are built using this FinFET device. Okay. The op amp circuits, in the op amp circuits you are going to have transistors. Those transistors are made up of FinFET device. Here you can see that how much N FinFET and P FinFET they have used, this on current, off current, the transconductance, threshold voltage, whatever subthreshold voltages are there, that they have values they use for making of these circuits. Okay, so here in this, so you can see this is nothing but your transconductance amplifier which is used in your op amp. So in that one they have used this FinFET circuits. This is a short gate FinFET because two gates they have connected. This is bubble one. You can see this is a P FinFET and this is a N FinFET. This is one gate and this is another gate. Two gates they are short circuited to behave as a made use for the op amp circuit. And here you can see that CMOS and SOI, the length of the channel they have watched, how much they have used. Length of the channel in the CMOS in the MOSFET they have used 1 nanometer. Here it is 30 nanometer. Supply voltage they have used. They have done with the visual TCAD this circuit zero point 0.5 and here also zero point 0.5. Gain here it is with the MOS. They got only 40 dB. Here with the FinFET they got 99.6 dB. That means it is more. It is a good performance it is showing. If you go for this, an example of analog circuit. Common mode rejection ratio is also good here. Power dissipation, if you see here, it is having 400 nanowatts. Here it is having 384 nanowatts. Noise also got reduced. Here it was having some 3.5 micro voltage. Here it is having 2.56 when you go. Noise figure is also very less when you compare to your MOSFET compared to your SOI. In the this is the earlier authors which they have done where you can find the reference 24 and 25. Okay. So how the frequency is, the variation of frequency gain is going to be varied. For the op amp, they have seen even the phase value, how it is going to be varied. They have checked this for different voltage values. This is variation of CMRR value with the frequency value and output and input voltages, how it is going to be varied. And this is all parameters which is related to op amp. They have checked here, which is used in the biomedical applications, instrumentation amplifier. Frequency variation with the power PSSR, power supply rejection ratio, how it is going to be varied. So as the frequency is increasing, PSSR they reduced with the FinFET. Okay. So this is nothing but noise level. As the frequency is increased, noise also got reduced. Here we can see the output of the op amp for in the instrumentation amplifier. This is the input and this is the output they are going to get. And this is nothing but your BSIM CMG file, which I told you. So you can you can write the direct spice codes for that device or the directly available PTM files. You can download from the internet from the Arizona State University. These are nothing but total spice. One parameter is going to denote one thing. Bulk mode. So whenever you are making, this is a one parameter. Bulk mode means whenever you are using bulk FinFET, this should be made one. Whenever you are using SOI FinFET, you have to make it one. So depending upon your behavior of your FinFET, different parameter values you can change and you can get the enhanced performance. Here for getting this performance, they have changed these values, whatever they have given. All these are different parameters, values which is given for your um, FinFET, for NFinFET and similarly for BSINFET. All this is nothing but parameter value which is given in the SPICE code or in the BSIMCMU files. Like this you can put the values depending upon the behavior and you can check what will be for these values, changing values for different parameters value. As you know, we have bulk mode, mobility is there, and next length of the channel is there, n gate reference number of gates, how much you are going to use, hmm, and length of the channel, fin height, width of the fin. In that spice code only you can change everything. Type 1 means which you are which type, one gate, two gate, three gates are you are going to use. That everything will be changed in this one. So like this spice code, you can make the circuits using the cadence or synopsis. Circuits you can do, and you are going to get good papers, and you can do a lot of good research in this field. Simply doing on the FPGA, Verilog, less papers in the good journals you will get. But upcoming whatever is there, if you do in this way, papers you can easily get good papers and good research you can do. So now, just I will just I'll give the overview why we are getting a low power and in the FinFET and nanowire FET. We have been saying that is going on saying that we are going to have low power, high speed and high security. What is the reason of this one? Because low power mainly we are getting is nothing but because it is going to have better gate control. Whether FinFET and nanowire FET, they are going to have gate is going to control from three sides or four sides over the channel, which is going to reduce the short channel effects because of gate control over the channel. Whatever the short channel effects are there, that is DIBL, punch through, subthreshold swing, all these are going to be reduced, and operating at lower supply voltage, we are going to have the low power. That is nothing but dynamic power. Next one, why it is how you are going to have the high speed. High speed we are going to have because of the strong electrostatic force which is present in the nanowire FET and FinFET. Because of the strong electrostatic force, it is making more current, more on current, and carrier mobility is going on. Carrier mobility is going to be more, which is going to have more fast switching, and it can operate at higher operating speed, which is going to result at the high speed. Why it is having low leakage? You are saying low leakage, isn't it? Because of the low leakage only you are having low power. Because using multi-gate structure. Why multi-gate means by using 2 gate, 3 gate and 4 gate, we are going to have the lesser subthreshold leakage, DIBL, less we are going to have, and leakage currents we are going to have. And how high security we are going to have. Because of the reduced power consumption and less leakage, it is not making the side channel attack. That means whatever is there nearby devices or nearby circuits or in the atmosphere, whatever the side channel attacks are there in the electromagnetic attacks, that is going to be will be difficult when the power is less or leakage is less in any
Hello, ma'am. Hello. Hello, Navneeta, ma'am. Hello. Uh, as we come to the end of this enriching session, it's my privilege to propose a vote of thanks. On behalf of Department of Electronics and Communication Engineering, MITW, I express our sincere gratitude to Dr. Navneeta ma'am for sharing her valuable knowledge, expertise, and insights with us. Feedback link has been shared in the chat box as well as it will shared in the WhatsApp group. Thank you once again for joining us. Uh, One request for everyone to just on your video so that we can share, take a pic of this. Hello, I request everyone to take on your cameras for once to take a group photo. Thank you.